All right, so here in section 2.5, when we're working with the absolute value equations and absolute inequalities, and again, we're wrapping up chapter 2 with this lesson here. There's some things we want to make sure we cover from the very beginning. For all real numbers x, we have to remember that the absolute value of x is also equal to the square root of x squared, because when you think about it, going back to earlier math classes, when we asked you to solve maybe by the square root property, we would bring the 4 across. We get x squared equals 4, and then we take the square root of both sides. And we said, hey, you know what? The possibilities here are plus or minus the square root of 4. And so x is equal to plus or minus 2 is what our answers are. And that kind of ties into when we learned about absolute values back in Algebra 1, that the absolute value of x is really either positive x or negative x, because I could stick basically, if I have an example here, if I said, well, let x equal 5, well, the absolute value of 5 is 5. And then if I said let x equals negative 5, the absolute value of negative 5 is 5. And so that's where we learn that if I have the absolute value of x is equal to a number, then technically x is equal to the positive or negative version of that number. And then that's the same case up here. When we take the square root of a number, we have basically two versions, the positive version and the negative version of it. Now that works just not only with the kind of a normal looking equation, but as we get more complex, the same thing applies. And so that means we have to work the problem 2 times, once with the positive version, once with the negative version, in order to find our potentially 2 solutions, and then we go back and double check the solutions to make sure they balance the equation or the inequality statement. So again, here they say, well, let k be some positive number, then the absolute value of our linear function, if it's equal to k, then that means that our linear function can be equal to the positive version of that k constant, or the negative version of it. Now notice it says if k is a positive number to begin with. So what that's saying is if I have like 2x plus 1 equal to 5, then I can go through and say this is 2x plus 1 equals 5, and 2x plus 1 equals negative 5. Now, if the beginning problem is the absolute value of 2x equals negative 3, then I can't do this. I can't solve that, because when we think about it, can the absolute value of a number be a negative answer? And no, it can't be. So here we got to be careful. That is when k is a positive number. So when the absolute value bar by itself is equal to a positive number, then we can say that the stuff on the inside is equal to the positive and negative version of the constant on the other side. So let's walk through some problems here, and we're going to work into the inequalities as well and do some graphing. So first thing I always like teaching my kids is to first look at the statement. Is it the absolute value equal to a positive number? Did we get rid of all the stuff on the outside of the bars and then make that decision? And yes, we do. So that means we write the problem down twice. Before we even start solving, let me put an x in there, equals 15. And 3/4 x minus 6 equals negative 15. I like writing down both equations at the very beginning. That way I don't forget to do one. Because again, we might have 2 answers here. And so we write both versions, the plus version and the minus version. And it's only the answer that is changing. It's not the expression. It's only the answer, the constant on the other side, that is going to be the positive version and negative version of it. And so let's go ahead and simplify. So add the 6. We get 3/4 x equals 21. I'm going to multiply both sides by the reciprocal, so that on the left side those cancel. I get x is equal to, well, 3 goes into 27 7 times, and then 7 times 4 is 28. Again, you could do keep, change, flip, same, change, whatever your middle school teacher taught you with dividing by a fraction. I just find it's easier with work showing is to go multiply by the reciprocal. So on the next one, we're going to go through and we'll add the 6 again. Now remember, that's a negative 15, so 3/4 x equals a negative 9. And then again, I'm going to multiply by the reciprocal. And on this side, those cancel. I'm left with x equals 3 goes in the negative 9. It's a negative 3. And then negative 3 times 4 is a negative 12. Now, what I'm supposed to do is go back and double check, does this balance the situations there? And so, we should always get in a habit of doing that. If I go through and say, okay, 3/4 times 28 minus 6, and then the absolute value of it. Well, 4 goes into 28 7 times. 3 times 7 is 21. And then the absolute value of 21 is 15, and that's what I have on the other side of the problem. On the other one, we would go through and say the absolute value of 3/4 times negative 12 minus 6, does it equal 15? And then we go through and say, okay, that's 4 goes into that. It's a negative 3. Then we have negative 9 minus 6. And then that's absolute value of negative 15, which we know is 15. And so, yes, it balances. And again, we should double check all the stuff that we're doing. All right, part B. This says the absolute value of 1 minus 2x is equal to negative 3. And this is where we have to stop and we go back and say, well, do we have a positive number on the other side equal to the absolute value bars? And this one we don't. So in this case, we would say there's no solution. There is no solution that will allow us to put a number in for x so that when we take the absolute value of it, it gives us a negative answer. Because when we take the absolute value of something, it's supposed to be positive. It's, and so forth. All right, so on C, as I try to give us some more room here, we see that the answer is equal to a negative 2. There's a negative k over there. The challenge is we don't have all like terms outside of the absolute value bars combined. And so we really can't stop and say no solution at this point. We need to, as we look at the up above here, we look at it, says just the absolute value bars. And that means there's nothing in front of it or behind it. So we have to remove that. So we need to go ahead and add the 5. And get the absolute value of 3x minus 2 is equal to 3. Now I can make a decision of, is this a no solution or do I need to keep on working? And then as I look at this one, since it's equal to a positive number and the absolute value bars are isolated, then that means, hey, I can go ahead and say, well, I have considered up as 3x minus 2 equals 3. And 3x minus 2 equals negative 3. And then we can go through and start solving for our answers as we go through the process. And then we should always check our answers. I'm just going to go through and solve, and just for time's sake for the video. Remember, it's okay to get decimal or fraction answers. And again, I would leave this as a fraction. I would not go ahead and turn it into a decimal unless they tell you to round. The majority of the online homework programs will want you to leave it as a fraction. As like when we're doing this section here. Okay. All right, so now let's see it in a word problem format. Remember, you can always pause, rewind whenever you need to go back and look at something, slow down the speed or speed up the speed of the video. Here it says the maximum and minimum lawful speeds S of a interstate highway satisfy the following inequality statement. Interpret this absolute values equation. Find the max and minimum speed. Okay. So when we look at the hardest part here is the interpretation. And so here, I'm going to find the answers, and then we're going to go ahead and look at the interpretation, that part. But basically what they're saying is our range of speeds, for lawful speeds is going to be within 15 miles an hour of the 55 miles an hour is what it's what we're kind of interpreting it as, is the minimum and maximum lawful speeds are within 15 miles an hour of the posted speed limit 55. So they want us to go through and solve those. So we get to, since that absolute value bar is isolated and it's equal to a positive number, we can say S minus 55 equals 15, and s minus 55 equals negative 15. We then add the 55 across, and we get s is equal to 70. And then we add the 55 across on this one, and s is equal to 40. So the minimum lawful speed is 40 miles per hour. The maximum lawful speed is 70 miles per hour. Now, does that mean to say that, you know, if it's posted as 55 degrees or 55 miles an hour, because that's what it's saying in the thing, the posted speed limit is 55, but it's acceptable in a way to go up to 15 over, that doesn't guarantee a cop won't write you a ticket. It's just saying that, they're saying the maximum minimum lawful speeds are this. I've seen it on highways that sometimes it'll say the minimum speed is like 45 miles an hour on a highway, and so forth. So, but that's how we go about solving it. All right. So now, then a variation of the absolute value is what happens when you have two absolute values on in your problem, one on each side. So what you have to do here is you have to pick one of the sides gets the plus and minus in front of the equation. So what I'm going to do is as I go through this, I'm going to write down the left side each time. So the 20x minus 40. I'm going to set it equal to the positive version of the right side. And then I'm going to write down the left side again, just the way I see it, and set it equal to the negative of the other side, which means negative, and then we got to distribute that negative. So it's almost saying the absolute value of 20x minus 40, is equal to plus or minus the whole other side. That's in a way what we're treating it like. Again, you can do either one. It doesn't matter. You can rewrite the right side twice the way it is and then put a plus and minus in front of the left side. It really doesn't matter. Now we need to just go ahead and solving, and then we got to double check our answers to make sure they balance. And so, with that in mind, I am going to subtract the 20x, and I'm going to add the 20. So subtract 20x, add the 20. And let's see, those cancel. Negative 40 plus 20 is negative 20. This gives me 60x. And then when I divide by 60, negative 1/3 equals x. On the other equation, I need to distribute. So 20x minus 40 equals negative 80x plus 20. And then I'm going to add the 40. I try to keep everything positive if I can. Helps with the inequality stuff we're going to do here in a moment. So this gives me 100x equals 60, and divide by 100. X is equal to 60 over 100, which is 6 over 10, which is 3/5. And again, we should always double check and see if they balance the original equation, is what we need to make sure we go back and do. So again, I know it's had this one up there, but we're going to just use this for work purposes as we go about it. Same thing goes on the next one. We go through. Again, it's a little bit more challenging just because we have the fractions in there, but the nice thing is they all have the same denominator. So again, I'm going to treat this as though it is like as what follows. Absolute value of 3/4 x minus 1/4 equals plus or minus the whole other side. So I'm gonna rewrite the right side twice, once with a positive version, once with a negative version. So 3/4 x minus 1/4 equals the 3/4 minus 1/4 x. And then I'm going to write it down again. And equal to the negative version. And then as I focus on the left one, I'm going to multiply everything by a 4. So I'm going to multiply everything by 4 so I can clear the fraction, because that's the only denominator I see. So that 4 cancels that 4. I'm left with 3x. Minus 4 and 4 cancel. I'm left with the 1. Equals 4 and 4 cancel. I'm left with the 3. And then 4 and 4 cancel. I'm left with minus x. And then now we get to solve this like a normal looking problem. And then I want to come over here and do the same thing, but before I start, I have to distribute. 3/4 x minus 1/4 equals negative 3/4 plus 1/4 x. Again, I am going to multiply everything by 4. 4's cancel. I'm left with 3x. 4's cancel. Minus 1 equals 4's cancel. Negative 3. 4's cancel. And then plus x. And then now I'm going to subtract the x and add the 1. Here I get 2x equals negative 2 divided by 2. X equals negative 1. And again, we should go back and double check our two answers to see if it works out to be the way it is. If I put a 1 in there, I have 3/4 minus 1/4 is 2/4. And then the same thing would happen if I put the 1 in there, I get 2/4, so it does balance. Put a negative 1 in there, I'd end up having a negative 4/4, which should be negative 1. Absolute value of 1, negative 1 is 1. On this other one, I put the negative 1 in. It would be 3/4 plus a 4th, which is 4/4, and the absolute value of 4/4 is just 1. So they both are solutions, but we should get in the habit of checking them. All right, now, a little bit different when we're dealing with inequalities. And we got this little section here. We'll do a few of those. And then we will also do a couple word problems down there. And I put some little notes at the bottom, just kind of wrapping up at the end of the section what all the little things, an example of each one done for you that you can use if you want to. So what they're saying here is, let our solutions to the absolute value of ax plus b equal k. We know it's two answers, S1 and S2, where one answer is less than the other. Again, think about it. My last problem I just solved, here is one answer, here's the other answer. One of them is smaller because with negative 1 is smaller than positive 1, so that's what that's saying there. And they're letting us know, again, remember, k has to be bigger than 0. So k is a positive number. Now, if we have the absolute value less than our positive number in our beginning statement, well, that's the same thing as solving this as this type of a compound inequality. And if we have the absolute value of our linear function is greater than a positive number, then it's like solving this type of compound inequality. And so you can use that format if you want. And again, it's letting us know that, hey, even if we have the equal to symbols on there, the same things apply. What I like doing is I like doing the process of, well, when I write down my problem, I know I see it, the absolute value is less than 8. So I write it down once the way I see it. And then when I write it down the second time, because of that, remember, the 8, when we rewrite it, is a plus or minus 8 when we go to rewrite it. When I go to do the minus part, I make it a negative 8, we have to remember, well, how does a positive 8 become a negative 8? Well, I multiplied by a negative 1. Well, that means when I multiply by negative, it switches the inequality the other direction. So it's got to face the opposite direction. And then now, as I go about solving, we add the 1. I get 3x is less than 9. and then divide by 3, and x is less than, less than 3. Here I would add the 1, and 3x is greater than negative 7. Divide by 3, x is greater than negative 7/3. Now, there we have two answers. We're telling our readers on a number line that x is less than 3, so here's 3. It's less than 3, and then there's technically an and here, and it is greater than negative 7/3. And that's why they're saying, you know what, if I notice that it's the absolute value is less than a number, so we match that first one, we could actually set this up as 3x minus 1 is less than 8, but it is greater than negative 8. And we can treat it like the compound inequality we did in our class, the previous section. We'll try that with number 88 is what we'll go through and try and do it that way. Number 83, we fall into the category of this next one here, which means that as I go to write it, I can write it as negative 5 minus 2x is greater than 1, or negative 5 minus 2x is less than negative 1. And so I have to write it both ways in that statement. And then now as I go to solve it, I add the 5, negative 2, add a 5. Negative 2x is greater than 6. I divide by a negative 2. I get x is less than negative 3. Remember, it flips over. We reviewed that in our previous section. On the other one, I have plus 5. Negative 2x is less than 4. And then I divide by negative 2. And I get x is greater than negative 2. And so when I graph this one, we are less than negative 3, so here's negative 3. Less than, it means this way. Greater than negative 2 means there's negative 2, and that means that way. And an OR graph kind of looks like what I always indicated in my classes before is what we call a rowboat OR graph. Like when you're on a rowboat and you have your oars pointing opposite directions. That's what the OR compound inequality should be graphed like on a number line. It kind of looks like the rowboat oars. Whereas the AND compound inequality looks like a set of the barbells, is what it looks like. All right, number 88, I'm going to go through and solve it by using the little process up above here, since I noticed that it is less than negative 2, and then I stop and I think about it for a second. Can the absolute value of something be less than a negative number? No. It can't be. It also cannot be equal to a negative number. So on this one, we would go through and say no solution. I don't even have to start the process of going about doing it. On 89, I have to add the 1 first before I make a decision. Can I keep on going? And then here, as we look at it, can the absolute value of something be greater than or equal to a negative 1? Well, technically we can be greater than a negative 1, but we can't be equal to it. So this is another no solution. So I don't have to keep on solving this one. Let's write those little if we have an example of the absolute value of like 2x plus 1 is greater than negative 2, so it's greater than a negative number, now keep working. Now we can keep working this problem. Because yes, a positive number is bigger than a negative number. Okay, so you got to pay attention to, it's okay on the inequality statements for a negative to be on the other side for the constant k. We just have to be careful of if it's the equal to bars on the problem or not. If it is, then no, we cannot do it. If it isn't, then we can go ahead and keep working the problem. All right, word problems. So the temperature T in a freezer is always within 5 degrees of negative 10 degrees Fahrenheit. Write an absolute value equation. Well, I'm going to underline this. The within 5 degrees, that's the part that's on, that's our constant K. That K, our K in our problem, that is 5. So our absolute value would be the temperature, and then what are we fluctuating around? What number is in the middle of the plus or minus 5 degrees? Well, that was negative 10 degrees Fahrenheit. So we would go minus a minus 10. So our inequality statement is T plus 10 equal to 5. A little bit different there as we think about it. But again, you know, it's, you know, when I go through and solve it, if we think about if it's within 5 degrees of negative 10 degrees, so negative 10 degrees, if that's in the middle, within 5 or 10, so if I add 5, that gets negative 5 degrees. If I subtract 5, that's negative 15 degrees. And then when we go to solve our problem here, T plus 10 equals 5, T plus 10 equals negative 5. When I subtract, I get T is equal to negative 5, and on this one, this gives me my T is equal to negative 15. Now, what we should use is we probably should use an inequality statement here because it says within, so that means, hey, that's the max it could be. And so what we want to do is we want to use the less than or equal to on this one is what we want to use as our inequality statement. So, so we're going to change all those over. Because otherwise, if we don't use that one, if we use the other one, then it could be greater than it. So, which will be pointing away. It'd be doing like an OR graph is what ends up happening. We want to be between those two numbers. Whereas if we use this symbol, then it's saying it's everything below negative 15 and everything greater than negative 5 degrees. So that's why we didn't use that symbol. All right, let's skip down here. Let's look at this word problem here. They asked us to identify the x and y intercepts. Again, we'll focus on doing number 19 is what we'll focus on here. X-intercept, I'm going to go ahead and circle them real quickly. Boom, there and there. So our x-intercepts are 0, 0, the origin, and 2, 0. Our y-intercept looks like it's the origin, so it's crossing there. So there's our y-intercept. Determine the values that satisfy this one here. So when they say determine the x values, so that we're writing intervals such that, well, when is the graph positive? So when this tells me graph above x-axis. So, well, I'm above the x-axis as I erase my two little circles here. I'm above the x-axis in this section and in this section. That's when f of x is positive. It's the answers are positive y values. It's this section as well. So for that part, f of x is greater than 0 from negative infinity to 0, union from 2 to infinity. So the next one said that would be when is it negative? When is it negative? So when is it below? Well, it is below in this highlighted yellow part. That's when it's below the x-axis. So when is f of x less than 0, which indicates below the x-axis, it means it's negative y answers. Well, that's between 0 and 2. And then when does f of x equal 0? Well, f of x equals 0 at the x-intercepts. So 0, 0, and 2, 0. How do the x-intercepts relate to the solutions of the equations in part C? Or in part B, sorry. They are the same. The solutions are the x-intercepts. And that's what we've tied that before in other classes, that there's multiple ways to say the x-intercepts, their solutions, they're the zeros, and so forth. Where is the function increasing or decreasing? Okay, I'm going to erase my drawings here. We can tell that as we come in from left to right, I am decreasing, I am increasing. So it is decreasing from negative infinity to positive 1, which happens to be where the vertex is, 1 comma negative 1. We are increasing from 1 to infinity. All right. Part E, is the function f ever positive and decreasing on the same interval? Sure, that's true. There's a time when it's happened. When we look at it, as I draw in, we are technically decreasing coming in on this side, and the y values are above the x-axis. So technically from negative infinity to 0, f is decreasing and positive. And we could say the same thing of with, is there any times when it's increasing and positive? So that's over here, increasing and positive, and from starting right there. And then in the small little v part in the bottom, we could say decreasing and negative on that little section there from 0 to 1. And then here we are increasing and negative. Now they asked us to do the domain and range of f. Well, as we look at the picture, it is a absolute value equation, and then in this case, my domain is negative infinity to positive infinity, and my range, well, it's not everything, because we notice it doesn't go past this y value, so it is from negative 1 to infinity because it points up to the sky. All right, so again, if you have questions, reach out.